So the agenda for my talk, I'll be giving an overview of the architecture and diving into some details as to why we made certain architectural decisions before getting into some of the key functional units in the chip. And then finally, I'll be talking about how our architecture also allows us to scale very efficiently to a system of thousands of processors. So I'll begin with this diagram of our packaging hierarchy, and it begins with the foundational building block of all of our product offerings, which is the GroqChip. We take this GroqChip and we package it into Groq cards, and then 8 of such cards are found in our Groq node. Finally, we have 8 plus 1 redundant node within our Groq rack, which is available in the ALCF system. So I'll begin by focusing on the left-hand side of this diagram, the GroqChip and the architecture behind it. So the soul of the tensor streaming processor architecture is fundamentally its determinism, the predictable nature of its execution, the predictable data movement on the chip. And that predictability really empowers our software and empowers our compiler to be able to efficiently map workloads to the compute units on the chip. Now, this doesn't only empower our compiler, it also allows us to achieve predictable low latency execution, which is critical for many inference applications. And finally, interestingly, this predictability we find allows us to actually scale in an efficient way to systems, as I alluded to, of thousands of these processors. And I'll get into some more details, of course, throughout this talk, but I'd like to just contrast this notion of determinism or predictability against more traditional compute platforms like GPUs or CPUs, which are inherently non-deterministic in nature. They often consist of an array of cores that are operating asynchronously with one another. They have, dynamic reactive hardware components that just inherently introduce non-determinism, which makes it challenging to program fundamentally. The challenges of parallel programming are well understood, and a lot of the reasons behind those challenges is this asynchronous nature of execution of these traditional architectures. So it also makes it harder to, of course, achieve predictable latencies. You see wide ranges or wide variance of latencies of execution of these platforms, and also fundamentally causes challenges for efficiently using these platforms, again, due to this asynchronous nature of execution of these platforms. And I get into more detail on the importance of predictable compute in this era of data flow compute in a talk I gave around this time last year. So I won't get into all the details of that talk, which is why I'm plugging it here, and I encourage you to check it out. It's available on our YouTube page. This is a slide I pulled from that talk, which is just highlighting essentially that with the era of data flow compute and the emergence of sort of static graphs of operations that we find in modern deep learning algorithms, as well as HPC algorithms, there's an opportunity for predictable compute, but it's limited by the fact that the hardware is unpredictable. And that's what's caused the challenges in developing automated compilers for these systems. And so at Groq, we've sort of taken this from first principles and understood that you need to offer predictability not only in the algorithms, but also in the hardware to achieve a automated compiler like the one we've developed at Groq. So again, I encourage you to check out that talk. I go into some details on this topic. So this is an overview of the first generation of our GroqChip. It's essentially a spec slide that you see for any of these accelerators. It talks about the amount of compute bandwidth, memory bandwidth, and IO bandwidth available. But I want to go a little bit deeper than just the specs. I want to get into sort of the foundational structure of the architecture and how that really empowers our compiler. So the foundational building block of the tensor streaming processor architecture is the SIMD functional unit. Each of these functional units executes a set of vector operations and is supported by a very lightweight instruction dispatch unit. So you can think of this as our base class of our architecture, if you will. And what we do with this base class is we specialize it into various different types. And here I show 4 examples of types that we see in our architecture. So we have our MXM, which is responsible for matrix vector and matrix multiply operations. We have our VXM for vector operations, our SXM for data reshaping operations, and finally our memory units that provide high bandwidth on-chip SRAM. So what we do with these various different types of functional units, we stamp out multiple copies of them throughout the horizontal dimension of the chip. with more copies of a given functional unit type offering more concurrency for the set of operations that functional unit type supports, right? So now I'll bring back the instruction dispatch units. Each of these functional units have their own instruction dispatch, but importantly, each of the instruction dispatch units are executing in lockstep. They're issuing instructions to their respective functional units in sync. And so this creates effectively a common time domain across functional units, which we leverage as part of our compilation process. So our first generation of our Groq architecture consists of 144 functional units and therefore 144 instruction dispatch paths. And for every cycle of execution of a program, each dispatch path issues a single instruction for every single cycle. Now, additionally, we'd like these functional units to be able to communicate with one another in an efficient way. We don't want them to always need to necessarily, go all the way back to memory and then back out in order to pass data between the two. So instead, we introduce these high bandwidth stream registers for data passing between the different functional units that share, again, this common time domain. So this is sort of a high-level overview of the architecture. And now I'd like to get into how this architecture actually empowers our software stack, our compiler. And I'll begin with the memory architecture. So the TSP architecture very explicitly, intentionally gives full control of memory to software. So what this means is there's no dynamic hardware caching here. The compiler is aware of the physical locations of all pieces of data that are stored in memory throughout the execution of a program. This additionally means there's no memory hierarchy here. There's no L1, L2, L3. It's a flat memory hierarchy that exposes the addresses of the physical banks on the chip to the compiler. So the compiler can physically address the banks. There's no form of indirection happening here. Additionally, the memory architecture also provides a very large amount of on-chip memory capacity. So first generation has 220 megabytes, but crucially, it also offers very high bandwidth, up to 80 terabytes per second of bandwidth available on the chip. And this is crucial, we find, because it allows us to saturate the compute on the chip, achieve a very high compute efficiency, even for workloads that have a very low operational intensity. And this is a characteristic that often exists in inference workloads, especially most recently in LLMs. I alluded to this earlier, but I want to double click on this. Our functional units are executing in lockstep. And what this does is it really empowers our compiler to perform cycle accurate instruction scheduling across both time and space. So you can think of this as synchronous execution of the various different compute threads on the chip, where again, each dispatch path is issuing a single instruction for every cycle of execution of the program. So this gives the compiler full control over managing instruction scheduling throughout while compiling a program. So beyond the benefit for a compiler, an additional benefit is actually this scheme happens to be very cheap to implement in hardware. Only less than 3% of our silicon area is dedicated to our instruction dispatch, which allows us to really maximize the amount of silicon area that we dedicated to raw compute and memory. Additionally, the interconnection fabric on the chip is intentionally made very simple. It's a one-dimensional interconnect, which allows our compiler to very quickly reason about all data movement between the functional units on the chip. So this interconnect consists of two paths. It consists of an eastward path and a westward path, where each of these paths of communication consists of a array of stream registers, where each of these stream registers is effectively a one cycle hop along that path. And so the thing to highlight here is that there's no complex hardware components. There's no reactive hardware components in the interconnect, right? There are no arbiters, no queues. And this allows our software to very easily reason about data movement without the need to perform any type of expensive cycle accuracy simulation. So this not only allows the compiler to efficiently manage data movement, it allows it to do it very quickly and allows us to maintain very quick compile times. So for example, if the compiler is trying to reason about data communication between two functional units, it's as simple as doing a single add or subtract operation based on the relative positions of the functional units on the chip. So putting this all together, the various features of the architecture that I just described, really the intention is to give full power of data orchestration to the compiler. And this is really illustrated by this animation that I'm showing here. So what I'm showing here is a program that was compiled and generated by the compiler, and it was never run on hardware. It was never run on hardware and profiled. This is simply our Groq view tool, which is available as part of our SDK. And we'll be speaking more about this tool later in the workshop. The tool is taking the information provided by the compiler and simply naively visualizing it, right? So this is really illustrating that the compiler has all the information about the entire execution of the program. There's no decision-making happening in hardware. All the decisions have been done statically by the compiler. So it's kind of cool, I think, if you sort of took this animation and you froze it, let's say, at cycle 2000, without needing to replay the events that happened prior, you would be able to see, because the compiler has this information, the exact location of all pieces of data at that moment of time, the exact instructions that are being executed, what functional units are being used, if data is being stored in memory, what addresses are being stored in memory. All of this information is statically available because it is managed by the compiler. And again, this is illustrating the amount, the full capabilities and power of data orchestration that has been given to the compiler by the architecture. And the intention by providing all this information to software is it allows it to optimally leverage and utilize the available hardware for the compute. All right, so we've talked about the architecture at sort of a high level and spoken about it in a sort of a macro sense. I'd like to get into some details on the functional units themselves that we see on the chip. So before I do that, I just want to highlight or emphasize that the tensor streaming architecture has many, great features, but in essence, it is a vector processor. So the fundamental unit of communication on the chip is the vector. And in our first generation of our architecture, that vector size is 320. And so these vectors throughout a program are streaming across the functional units using our stream registers. And as they pass through functional units, a functional unit can pull that data off, do some processing, and then put it back onto the stream registers to continue the execution of the program. And so our various different functional units I've sort of highlighted here. I'm going to sort of go through them one by one. And so the first one I'd like to highlight is our MXM, or our matrix multiply engine. This is really the workhorse of the chip. It offers very high amounts of compute bandwidth for the critical matrix, and matrix vector operations that you see in modern deep learning workloads, for example. So in our first generation of our GroqChip, we have two such MXMs, one in the Eastern Hemisphere and one in the Western Hemisphere. And each of these MXMs support two numeric modes, int8 and float16. And some details behind this, in int8 mode, each of the MXMs supports a 320 by 320 matrix multiply, and it can do two of these matrix multiplies concurrently on each MXM. And so it offers sort of tons of bandwidth at int8. And the resulting tensor is int32, which is just highlighting the accumulated data type that we use in the MXM. And for float16, it offers you higher precision at slightly lower, or at lower bandwidth compared to int8. So the matrix multiply size is 160 by 320 here, only one of which is done per MXM, and the resulting data type is float32. Next, I'll go into the VXM. So this is our vector unit, and it supports a wide array of vector operations, arithmetic operations, logical operations, bitwise operations. The TSV is fundamentally, it is a Turing complete machine. So you can compose these operations to support any type of compute you might want to do on the chip. And what's interesting to highlight about the VXM is it consists actually of an array of ALUs that could be chained with one another to form more interesting units of compute. And so I'm showing you an example here where we've combined essentially 4 operations within one pass of the VXM. So we have a reduction operation initially where partial sums are reduced. And then that's followed, for example, by a bias add, which is followed then potentially by some type of activation operation like a ReLU. And finally, you might want to cast the output. And so another ALU can be used for casting to the data type that is expected for the next operation in the program. So what's interesting and important to highlight here is by chaining these ALUs together, we can really achieve very high amounts of vector-vector bandwidth as well. And what's really cool about our software stack is it is able to do this type of chaining automatically. Next, I'll get into the SXM. So the SXM is what empowers us to do data reshape operations. So I mentioned earlier that fundamentally, this is a vector processor. And for vector processing, you often have to do permutations or manipulations of how data is laid out within the vector. And the SXM is responsible for doing so. And so within the SXM, we have various different functional units that allow you to do this, these type of operations at various different bandwidths. So we have our distributor units, and they're responsible for doing very high bandwidth permutation, but within 16 byte parts of the vector, or 16 element parts of the vector, I should say. We have additionally the transposer, which allows you to do matrix transposition. So you can stream in a set of vectors that form a tensor, and that tensor can then be transposed by the transposer. We have the permuter, which is able to do any arbitrary permutation of the vector, but it does that at a lower band with respect to the distributor. So depending on the type of permutation that is needed, you can opt for the higher bandwidth distributor or the lower bandwidth permuter. And I'll also like to highlight that the permuter actually also supports shift operations at a higher bandwidth as well. So if you'd like to shift the vector upwards or downwards, depending on the shift amount, the permuter can do that operation as well at higher bandwidths than just an arbitrary permutation. And so the combination of these units allows the software to consider what type of unit to leverage based on the operation that's needed, and therefore optimize for the bandwidth that it can leverage based on what's required. So it can choose between using the distributor, transposer, permuter, shifter based on the operation that's needed in the workload. Additionally contained in the SXM is our IO units for accessing our chip-to-chip communication. And I'll get into that in a little bit more detail in a couple slides. Finally, and I've already sort of spoken to this already, but of course we have our memory units offering lots of on-chip capacity and bandwidth. And just to highlight, how exactly this is implemented, our memory is implemented with a wide array of memory banks. And the sheer number of banks is what is allowing us to offer such high amounts of bandwidth. So we refer to a unit of memory as a memory slice, where each slice has 2 memory banks within it. And then we have 88 such slices across the chip. And so you can picture this as a very high amounts of bandwidth offered due to the amount of banks that we have. So this is where we get the 80 terabytes per second of bandwidth. All right, so up till now, we've spoken about the architecture within the chip. We've talked about, macro level, why we made certain decisions. We dove into some of the functional units. But now I'd like to talk about how we take the architecture and we leverage it for scaling to a system of thousands of processors, which is really, I think, one of the key superpowers of the architecture. So again, we talked about the left-hand side of our packaging hierarchy. Now I'd like to focus on the right-hand side, how we scaled, within a node, within a rack, within even a system of many, many racks. So the Tensor streaming processor architecture employs a synchronous chip-to-chip communication paradigm. Now, what I mean by this is the architecture provides a chip-to-chip protocol that employs a plesiochronous communication system, where the protocol can deterministically account for any natural clock drift that occurs across the TSPs in the network. So that's natural to happen. The clocks are not perfectly going to be in sync due to deviations in the crystals, for example. And our protocol actually deterministically accounts for this to expose to our software stack a fully synchronous network. So what this means is the compiler statically at compile time can understand that if it's scheduling data to be sent from a source TSP at cycle n, that data will arrive at exactly cycle n plus some known value L. And it determines this at compile time statically because of the synchronous network that is exposed to it by the chip-to-chip protocol. So this is quite powerful and allows the compiler to sort of globally manage all the network traffic throughout the execution of the program. Now, to enable this, additionally, we have to employ what we refer to as software scheduled direct networks. So what this means is we can't have any dedicated router chips, which would not be under the control of the compiler and may introduce dynamic, reactive hardware components that would not be statically resolvable. And so to resolve this, we actually treat the TSPs as both processor and router. And that allows the compiler, as it generates programs and as it schedules programs, to not only schedule compute, but also schedule all network traffic throughout the execution of the program. So this is very powerful. We don't need any type of locally sensing routers that do maybe some fancy adaptive routing or congestion sensing techniques. The compiler actually has a global view of the network statically and is therefore able to optimally load balance the network links in order to maximize the efficiency of the system. And I highlight this here in a very simple example where you can compare and contrast a traditional non-deterministic network on the left here with a software scheduled network on the right. So the traditional network will have processors that are operating asynchronously with one another, and they may be connected to routers that are doing sort of local congestion sensing techniques. And there's this sort of delicate dance that's happening where it's sensing, locally, is there back pressure on a link? Should I, consider using another route to get to my destination? And this is sort of fundamentally limits the ability of the network to sort of optimally utilize the links in the system. In contrast, the software scheduled network has a global view at compile time and is therefore able to know if a given route is available when two processors want to communicate, and if not, choose maybe a different route, maybe consider non-minimal routes, for example, and can do this because the information is all statically resolvable and available to the compiler. And so the compiler, for example, in this example, can see processor B is communicating with processor D, so opt for a route that avoids processor B for the communication between processor A and processor D here. Now we combine the synchronous networking with a low diameter network topology, which is crucial for low latency inference. So the Groq rack, the Groq system, employs a dragonfly topology with local groups within each of the nodes that offer very high bandwidth within the group. So our Groq nodes employ 8 chips that are connected with an all-to-all network, or a 1D flattened butterfly, if you will, that offers very high bandwidth within the node. And then we have more sparse connections across the nodes to form the dragonfly. And a key feature of this network is it offers a very low diameter network, or a very low maximum hop count between any two processors in the system. So this is in contrast to a torus network or a mesh network that has a much higher network diameter. We opted for a lower diameter network to ensure that the latency of communication between any of these processors is kept very low. And so we combine the synchronous communication paradigm with this low diameter network to really achieve very high efficiency communication within our system. And this was highlighted in some results we published in our ISCA paper last year, where we showed how for common collective operations that you see in networking, such as all reduce, for example, we're able to saturate the network bandwidth available in our networks, even when the packet size is very low. So because we have low latency, we don't require as large packet sizes to amortize that cost of communication between any two processors. And so we show this in our results where for packet sizes as low as, on the order of kilobytes, we're able to saturate our network bandwidth. And you compare that against a more traditional non-deterministic network, it requires much larger packet sizes to amortize the cost of latency of communication between processors in the system. And this is all done by combining our low diameter network topology with our synchronous communication paradigm. Now, interestingly, this notion of being able to saturate your compute at low packet sizes is quite relevant as of late with the emergence of large language models. So if you're trying to do inference on large language models, you'll notice that the unit size of the all reduce operations that happen is very, very small. It is actually on the order of kilobytes. And this is, again, an advantage that we have in our Groq systems for inference applications like those needed for large language models. And if you've paid attention to some of our public material as of late, you'll have seen that we have shown this. This isn't only theoretical. We've shown state-of-the-art LLM inference performance on a system of 10 Groq racks. And so we showcased this on a Llama 2 70 billion model, and we showcased state-of-the-art numbers there. You've probably already seen this. We potentially are going to cover that in the workshop. I haven't looked at the schedule, but I do know that one of the sessions will be talking about how you can leverage a single Groq rack for Llama 2 7 billion. All right, so to recap what I've covered today, talked about the architecture and how it empowers our software thanks to key characteristics of the architecture, including its determinism or its predictability, the flat memory hierarchy, and the simple one-dimensional interconnect. We talked about some of the key functional units on the chip, the MXM, the VXM, the SXM, and our memory units. And finally, as I just mentioned, we talked about how the architecture allows us to scale efficiently to thousands of processors via this plesiochronous low latency chip-to-chip communication architecture.